Another thing that is very interesting to note that if we consider this equation, sorry, this power equation, you'll see that we'll be having three terms, right? One is due to IR, means all the terms like ohmic. Another term will be like P lambda I. They are power loss due to induced voltage. And the third one will be speed. We can write speed power. Slight abuse of means terminology, right? Speed power. So this speed power, what we can see here, that this speed power, the ultimate expression will have only the speed power term. The remaining term is p lambda I and I square r, they will some way cancel out each other, leaving us with only speed power term. And uh, that is we can do it mathematically, and also we can prove it, means we can intuitively try to understand this, because see, while if you are let us consider one situation. Suppose here is no omega term is here, right? No omega, as well as here you also have no omega. So your total power expression, forget about this torque, your total power expression is independent of omega. Your mechanical power is independent of speed. But that is very absurd, because when, as we know that during starting, or means before starting the motor, when the motor is in standstill, we have finite torque TST that is greater than 0, but PST is equal to 0. And that is very obvious, because power is equal to torque into into speed. So if you let your power free from your speed equation, or means its dependency on speed, you will not get a valid, means physically corroborating result. So that is why we have this term. And also here we can see one thing, that with our little mathematical manipulation we can prove this result. So what we are getting, we are getting this expression. Now what we can do more, in case of means steady state, few assumption we can have, and in case of steady state we can go for a per unit representation also. That is very interesting. See here we are writing this p lambda, that is ddt of lambda, that is means our induced voltage, induced voltage induced voltage across a particular winding, or say if you are considering psi as, means this psi as, it is like p lambda s. So this psi s is the induced voltage. And here another thing, as I have just mentioned, that psi is equal to omega b lambda. Now first of all, let us know what is omega b. Say suppose if you are dealing with Indian system, then your frequency f rated is equal to 50 hertz, sorry, 50 hertz, right? F rated is equal to 50 hertz. So this omega b, in case of India it will become 314.59 rad per second. Right. Now, this model is valid only for steady state. This is not valid for transient. Why? Because, like in case of series RL circuit, the generalized equation is L didt plus Ri is equal to V. But in case when you apply a steady uh, AC and when your system reach steady state, then you can write it is like the L plus R is equal to V. So this is quite an acceptable expression. Here you can in case of steady state you can have that P is equivalent to omega b, and dimension wise they are almost same, because this p, that is d by dt, means something having reciprocal of second, and this omega b is frequency, so they are quite means dimension wise they are almost similar terms, and this pb they are just means selected to adjust the, or means make the whole transformation more means uh, smooth and simple. Another thing here I'd like to mention, this omega bm, as we know, this omega bm is our mechanical base speed. Mechanical base speed, but or more precisely, this omega bm is our mechanical synchronous speed. It is mechanical synchronous speed. This omega bm is mechanical synchronous speed. Now, these expressions are quite clear to us, and this one, this psi qs, this is also easily understandable. Now, what is the essence of means deriving this whole thing? The essence is that with this we can model for our induction motor, a steady state model of our induction motor. Now, one thing here will be you'll notice that this one, this is this induced EMF, this like the vector of this like the sorry this like the vector of induced EMF. I indicate induced EMF, and the this is like previous r to the power 6, but this one, this is our reactance matrix having dimension, right, and this is our current. So we know that in case of steady state we can express our induced EMF like reactance into uh, ampere or current, right. So this is quite a valid expression, and this is our means all the terms derived, and we are getting the same result. Only thing, in the previous case it was this lm iq, means that whole thing was lm, and here you are having this, means you still have this omega b here. Now, this is the equivalent model. If you can trace the previous equation, what you will be observing that this VQS can be written as, from the very beginning we can trace this equation. Uh, which one? Just let me find out. Uh, yes, yes. I think from this equation we can explain. See, this lambda QS, right? This lambda QS is dependent on two current. One is IQS, another one is IQR dash. So from this now later on you can convert this lambda QS. Here also we have this like ls plus lm. Here we are having xls plus xm, that is associated with iqs, and this one is associated with iqr dash. So one thing that is very clearly and this is our induced emf, ie, sorry, there is a crack on my screen so I cannot write there. So this is our induced emf, ie, right? This one. So this ie here, one thing is easily understandable that uh, this ie, uh, the two current like iqs and iqr dash, if you compare, both are flowing through this one. So we can have a model like this where if this is the current through our IQS and this is the current through our IQR, we are having both of them are flowing through the same path. Here IQS, the total current is IQS plus IQR dash flowing through this, and that is quite a valid explanation. And in case you are dealing with a squirrel cage induction motor, this will be solidly short circuited. You will have VQR is equal to 0. This speed EMF will be utilized to supply your whole power. And see the interesting thing, the very interesting thing here, that if you make it short, what we know that if we allow our rotor to rotate at a speed, I mean synchronous speed, or there was a popular argument that why rotor can't, means in case of squirrel cage induction motor, rotor can't reach our synchronous speed. That obvious answer we used to give that in that case there will be no such relative speed, means if your omega r, if you make it like omega or omega e, then what you will have here, you will have zero current, and this total portion, this will just be behaving like a, means idle circuit, right? Now here see, this is another interesting thing, that this is the corresponding EMF that is in our q axis, and this psi ds omega omega b, this is our eqs, right? And basically you can say that this is just a scaling of your induced emf. If you make omega b is equal to omega b, that means if you allow your speed, or means basically it will become in that case omega e, that will give you the whole psi ds here. So it's very easy to understand that the total VQS what we are having here is like IQS RS plus XLS, sorry, and then here it will be like IQS plus IQR dash XM, right? And that is very interesting to note that total voltage it is having an the expression this IQR dash XM. So you can means although this will be just like a layman means guessing or trying to relate, or a blind person is trying to relate to total different thing, but there is a means analogy will get this IQR dash XM, that or means VQS. What is VQS? This VQS is your stator voltage. This VQS is your stator voltage. So this stator voltage is not only responsible for means overcoming the series drop or means transformation of power, but it is also responsible for your means whatever you are getting from your rotor, means the what we say that how if we put load then sleep will be means sleep will increase, and that with increase value of sleep the rotor current value will also increase, and that rotor will produce means huge demagnetizing action, and in order to means make that whole flux or keep that whole flux inside our machine housing complete, uh, stator will draw more current, and here you can get that means logic how the means stator will be drawing more current due to your rotor current, right? Now similarly we'll have our d-axis model, and d-axis will just be like q-axis only. There will be a change in our speed uh, means EMF. Here one thing I'd like to hear that all the time all means why the speed EMF that is in d-axis and q-axis they are different in nature. Why so? Now this is zero sequence, and as we have noticed here um, or everywhere that zero sequence, if you consider the row of zero sequence, only one element is present, that is XLS. Or similarly in case of rotor also you'll see that XLR dash this is only dependent on I naught R. So this is quite an obvious means uh, image or circuit representation we can have here. Now let us consider one more interesting case, that when our machine, our this is a q-axis model, when we have our omega is equal to omega e, right? When omega is equal to omega e, then what we'll have here means that omega is equal to omega e, no sorry, not omega is equal to omega e, rather I made a mistake, sorry, it should be like omega is equal to 0, right? If we make omega is equal to 0, then what will happen means if your means reference frame is attached with your stator axis, basically you are getting here, you can note this is basically a Clark model, means or a very simplified representation of Clark transformation. Clark transformation model of your induction machine. So here your omega, the reference speed, rotating reference frame speed is 0. So you can see here that all the speed term of your stator side is becoming 0. And I also told you that if you can recall, you'll notice that generally in case of induction machine, we don't get any kind of such back EMF term when we are means when we had not learned this reference frame theory prior to our means discussion when we were dealing with conventional way to analyze of induction machine. Then we observed that induction machine rotor means has nothing to do means it's not a back EMF, just transformer EMF is getting induced in your rotor winding, and that is ensuring a flow of current through your rotor. But in your stator phase there is no EMF is getting induced. But and the same thing you will have here, that when you will make your reference frame stand still, then all the and this is very similar to our means conventional uh, uh, per phase representation of single induction motor, where you have one current and that current is and if you want more similarity you can just short this, right? And also you will be observing this minus omega r by omega b. This minus omega r by omega b is basically nothing but, see the polarity of that voltage. This is plus minus. So basically when you'll consider this voltage will be appearing here like EQR. All right, when you will make this short, then this voltage will come here. So this is very means quite reasonable and obvious representation, and same thing will happen to our d-axis, nothing new. And means uh, one more thing here I would like to mention, that like our synchronous machine, our zero sequence network, we have observed that zero sequence is like he is like God, means no one and nothing can means disturb him. He is still unaltered by your choice of reference frame speed. It remains same. So same thing happens here. Whatever we were having in the past, means when we are having some value for omega, some definite value for omega, we have this one, and now we are omega is equal to 0, then still also we are having the same zero sequence frame, right? So this uh, like in the last video, we have observed that how we can represent our machine model in means standstill reference frame, and right now we are considering a frame that is rotating at a speed of means synchronous speed, like here your omega is equal to omega e, right? Now here one thing that is very interesting to note, that means by application of formula we can get everything, that see uh, can we do something to explain that if our synchronous machine reaches our uh, means speed, that is our what to say, that speed of our means synchronous speed, that means what I'm trying to say, if we can somehow make this omega e minus omega r is equal to 0, then can that means help us to explain that the torque that is will be produced by our synchronous machine will become 0? Can we do that? in any way? See, to answer our question, let us revisit one thing. Yes, so from this expression, what we could this means we can see or we can prove here that this one. Now, if you consider this equation and then if you go back to your original circuit, right, here, this one, you will be observing that when you will make omega r is equal to omega e, then this one will be behaving like a short circuit, means this will not be there, right? And whatever remains is these two element, series RL circuit. And in that case, first of all, uh, one more thing here, you have to make it short. So if you short, then you will see, you will get one expression, that is xm, xm in parallel with your xlr dash plus rr dash. So when you will see this xm parallel with lrr dash, then uh, xm parallel with lrr dash, then you will be able to understand this. You will find some value for your means the from this expression you will see that how the bracketed term will become zero, and you will have no torque coming out of your machine, right? Now see, this is our d-axis, and that means obviously when you try to prove that, means if our machine reach synchronous speed, it will, means the rotor reach synchronous speed, the net torque will be zero. You have to simultaneously deal with secondary short circuited d and q axis circuit, and you will get your answer. Zero sequence has nothing to do with that. And now after this, now before we go to transient, let me tell you a few interesting things. That is, if we consider that stator and rotor, for both of them, if we try to find out LR ratio, where your LR ratio of stator winding, let it be LS by RS. You will see this LS by RS for a, and the rotor one is LR by RR. You will see for high efficiency machine, generally rotor resistance is very small in compared, and that makes the LR ratio of means efficiently designed induction motor, LR ratio of rotor winding for an efficiently designed induction motor is very high. So what is the issue here, that if you can recall the time constant, the expression of time constant in a series LR circuit, basically uh, your three-phase induction machine, primary and secondary, not primary secondary, that stator winding and rotor winding, if you consider per phase winding, they are just like series RL circuit. So the series RL circuit means, by virtue of their construction, the way we have connected them or we have placed them, they are, means they are response, their time response, or the way their current is varying in the winding, will obviously follow this time constant formula, right? So what I'm trying to say here, that is very basic thing, that all the time this transient, this transient depends, or means we can consider that transient won't take place in two different type of circuit. One is where your LR ratio is very small. Why? If LR ratio is very small, then what will happen? The time constant tau, that is L by R, it will be in the order of a few millisecond, or like a tungsten bulb. If you switch on a tungsten bulb, then what you will observe that just the very moment you switch the power, switch the on your press the switch on your board, uh, the bulb starts glowing, and it is available to give you the full lumen output. So that is the implication, that if your R is very high and its L by R ratio is very small. And another kind of thing where you can have means you cannot avoid transient there, but the second case where your LR ratio is very large, is very high. In that case, what will happen? Suppose if you have a circuit where your LR, suppose if you assume one circuit like you have inductor, and then you say here you have a bulb, right? I am not good in drawing. This is our bulb, and here we have uh, DC circuit, right? So once we switch this one, sorry, once we close this switch, right, this switch here, then this circled one is indicating our bulb, that is almost, this bulb is more or less like R resistance, and this is L, and this circuit here, our L by R is very high. So in that case, if you switch on, then your bulb will take a huge amount of time to reach its full lumen value, because in that case your circuit means the bulb means steady state current. If that bulb resistance is R and if your input voltage is VDC, that voltage is VDC by R, this voltage will get typically after 4 LR, means not the full 100% of this you will get, rather 98% you will get after this 4 L by R time is lapsed, where L is in your Henry and R is in ohm. So this L by R ratio will give you an unit in second, and once this 4 L by R time lapse, then only your bulb current will reach 98% of this value. And that is why we can say that the circuit with very high LR ratio will take a huge amount of time. So if you have two circuit, one is having a small or a comparatively uh, nominal LR value, and another one which is having a very large LR value, you can consider for your operation time. Suppose we have two circuit, right? One is one bulb, and another one is one bulb plus huge L and this one plus small l, right? So this first case, sorry, in the first case, you can understand that this circuit, the circuit number 1 that is having small l, will reach its full lumen or will be able to reach its full lumen, and at that time you may consider that your second bulb that is connected with a huge L will be in means almost in a very dimmed state or means will take a sufficiently long time. So while you are dealing with one circuit transient, you can consider the other circuit has not yet switched or means has means I should not use that not yet switched, but I can say that it is means not exhibiting any tangible response, right? Any tangible response is not from our second circuit, but the first circuit is exhibiting tangible means response. Now, while in case of induction machine, do remember we means while doing simulation or everything, we always means prefer to consider ourselves as an observer from stator side, right? So, observer from stator side, what observer from stator side will see that the variation in stator current. So while you are trying to obtain a transient model and that suitably mimics or means reciprocate your circuit behavior during your means stage, means the stage that is transient stage. At that time, as I have mentioned, that rotor circuit LR ratio is very, very high. You can consider, try to pay your attention, this rotor circuit LR ratio is very, very high. So at the time when the stator current undergoes a transient state, you can consider your rotor flux linkage is sufficiently constant, means it will be varying, but that variation is so nominal, so small, you can disregard it, right? And that will help you to obtain a simplified transient model where you don't have to consider the means rotor transient while you are dealing with the stator current. Later on, you can obviously you can or you have the choice to means go for a more detailed, more enriched model. But for the first time, let us deal with that simple one. While we are considering the transient is means uh, being observed by the stator side observer, at that time rotor flux linkage is constant. So uh, we begin the derivation of this simple transient model by considering a perturbation to the variable and this expression, like we are considering this the four flux linkage term we are considering, we are not talking about the zero sequence. So with perturbation, what we'll be getting here, if you introduce perturbation in this four term, you will be getting a term like this. Everywhere you will have uh, this delta, this second terms, they are basically representing that means certain variation, and that is here we can see, right? And let me tell you one more thing here, like my previous every time I have made some type mistake, it should be delta here, another delta should be here. So this means circle term, they indicate the rate of change of flux linkage, right? Now what we know, that this last two terms, these two, as I have mentioned that LR for rotor is very very high than that of stator. So the last two terms and they are corresponding means the current, the rate of change of current that are responsible for production of them at the onset, or means when the stator circuit is undergoing transient, we can consider this part is equal to 0, and accordingly we can have our expression like here. This is the expression. Fine. So from the above relationship, what you will have, since these two are 0, so from this these two you will be getting uh, uh, this one, right? And here our main interest is to find out the rate of change of flux linkage in our means QD stator axis, right? So we got this expression, and if we go for separation of variable, that will help us to obtain this, right? Now the perturbance or this the pre-disturbance values of this flux linkage and current also satisfy our this means this set of equation. This all this equation must be validated by the perturbation of current, and what we'll be getting here from doing all this, like the previous case of our synchronous means machine, we can define our means transient, that is means stator transient inductor. Now see here, this stator transient value, inductor value, is same for, means it is unlike your synchronous machine where we had LDTR is not is equal to LQTR. That is very obvious because there was an uneven air gap exist. But here you can see that we don't need two inductance, rather one inductance LSTR, that is sufficient to represent our what to say that is stator transient inductance. This is a single inductance, sorry, this one, this LSTR, that is our, we define it like stator transient inductance, right? And accordingly we have to define, like the previous case, we have to define the voltage behind our transient inductance, and that is just the speed voltage, right? So this speed voltage we are getting here. Now this speed voltage, now from our this first set of equation, or rather this first two equation, and the uh, this equation, right, this equation, what we can do, will be able to express this speed m in this form, right? Just a small mathematical manipulation can help us to reach this derivation, where both of them are dependent on our supply frequency, supply omega frequency, and Another thing, as I have already mentioned, that this LM, LR dash, lambda dash EDR and lambda dash EQR. So this is quite obvious that when the rotor flux linkages are constant, the means if you keep this rotor flux linkage constant, then this voltage behind the transient will remain constant. And that is also means physically understandable means reasoning, because if you keep your rotor flux linkage constant, then whatever voltage is induced across your rotor, that will remain constant. So what means you will act means see, it will be like this one, that the total thing, your stator uh, rate of change of flux linkage can be expressed by this expression. Stator rate of change of flux linkage can expressed by these two equations. And one more thing here you can observe, that this equation is very interesting to know, that we can have a model like this, where this one is constant, this is constant. What is the means, then you may ask me that why this is the transient model. It is like you are having two AC voltage and one is AC voltage of different value, and you are connecting them with RL circuit, and you want to means observe the variation of this current. That is the how this transient will be varying. And it is obviously in case of your induction motor, suppose suddenly you put some load on your induction motor, then what you will be observing? Basically you will be observing that your current undergoes, your stator current undergoes a certain transient state. So when you will observe the transient state, as that means intuitively you can understand that transient will take place through a series RL circuit. And uh, suppose if you put some load on your means induction machine secondary, then you will have a different voltage across your rotor means uh, one side of that RL circuit, and you will have two different voltage across your RL circuit. Means what I'm trying to say, let me write, then you will get it clearly. Like you have one RL circuit, here you have one voltage Vs. Now if you keep this Vs constant, and suppose here you have Es. Now, if you change this ES, means when you will means put some load on your motor, then obviously there will be a change in this E, and this ES, what you will observe, there will be a current surge, means or a current reduction in your current due to this change of ES value. And that is why the transient model, even it is virtual model in QD0 frame, we get the similar kind of means explanation or means variation. So this is all of our means transient model. Now like synchronous also, we are not interested in finding out time constant, you can easily do it. So the assignment which I was talking about for synchronous as well as for induction machine, you have to find out the steady state model. And if you are means too lethargic to do or derive that by your means oneself, then what you can do, you can go to this book of Chi Moon Ong, and you can download that and open chapter number 6 and go to article 6.6 or page number 198, then you see that steady state model is there. But what I want, that I want at least you do it, and while at least the willing students will be sending the or will be participating in the exam will send me either by analyzing by his own effort or by means copying it from the book. They should send it to me, and that will be appreciated. But again, I'm telling you, there will be no such hard and fast rule that you have to submit, you have to participate, because all of us are undergoing a difficult time, or means I cannot force you to means if you find enough free will to do this, then only you should participate. But one thing that is very important, that if you participate, you will learn, and means you will get a better grip on this subject. And this is a very good topic, this reference frame theory. Everywhere you go, everywhere, everything you do, whether you will do a project on solar panel or anywhere, everywhere you will find the application of this reference frame theory. So this is all about our means reference frame theory.